So the first couple of things are just some reminders of some definitions. First is polynomials. Of n degree can be written as f of x, and then this should actually be an equal sign, not a negative. Equals ax to the n, bx to the n minus 1, plus c n to the x minus 2, dot, 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 dot. So it's just saying you can have coefficients, you can have exponents. The exponents tend to decrease, and exponents have to be whole numbers. So everything you know about polynomials, that's all this is saying. Leading coefficient, just a reminder of that. We looked at that last unit when we looked at horizontal asymptotes. And figuring out leading coefficient is the coefficient of the term with the highest power. It's called the leading coefficient. And the graph of a polynomial, which you know from drawing quadratics, is smooth and continuous, so it has no asymptotes, no holes. It's bumpy. It's got maxes and mins, just like parabolas did. So what we're going to do is just start to compare what we already know. We're going to look at a first-degree polynomial that you did in grade 10. We're going to add a second-degree polynomial, which you did in grade 11. We're going to add the cubic that we talked about in Unit 1. And then we're going to add 4 to the 5, which are brand new. So we're just going to build upon what you already know. Tell me about a first-degree polynomial. What did we call it way back in grade 10? Linear. It's a linear function. And this was that y equals mx plus b that you probably hated at the time, but now in hindsight it doesn't look so bad. And this form was called slope-intercept form because m is the slope and b is the intercept. But there was another form that we called standard form, and it looked like ax plus by plus c equals 0. You kind of remember that? Little tiny bit back in your brain somewhere? Now, this leading coefficient stuff we didn't really talk about in terms of linear functions. So I'm just going to throw it in now. This means positive leading coefficient, negative leading coefficient. What this means is that m is a positive number or m is a negative number. So leading coefficient is on the x because it's x to the 1, and it was either positive or negative. So tell me, what did a line look like that had a positive slope? Show me with your hand, show me with your arms, draw it in the air. Show me a line that had a positive slope. Yeah, so we know that it increased. It was like going up the mountain. Started at the bottom left, went up towards the top on the right. What if the slope was negative? Show me with your hand, show me with your arm, draw it in the air. Okay, so it went down. It was like skiing down the mountain. And so we're going to start to talk about what's called the end behavior of a graph. And what that means is, what is the end doing on the left and what is the end doing on the right? Is it going down or is it going up? If we look at this left-hand side, we say that the left-hand side is going down. It's decreasing. If we look at the top, the right side, what's happening? It's increasing. So we would say the end behavior of this graph is down-up. The left-hand side is going down. The right-hand side is going up. That's called the end behavior of the graph. Well, what's happening over here with the negative leading coefficient or negative slope? The left-hand side is going up, and the right-hand side is going down. So we call that up-down. Okay, it's called end behavior of the graph. It's just which direction is the ends of the graph pointing at. And so what we're going to start to do is look at some patterns, what's happening here. Okay, second-degree polynomial. We did these to death in grade 11, like 4 units on them. What did we call them? Parabolas. Not parabolas. That sounds like a disease. It's a parabola. What was the other name? So we called them something else as well. Quadratic functions. They were so important, they got 2 names. And so it had the form that looked like y equals a bracket x minus h squared plus k. Hopefully that looks familiar. And we talked all about the vertex and the width and all those great stuff about parabolas. But it also had a standard form. It was ax squared plus bx plus c equals 0. And those were those equations that we hated to factor because there's so much work, so they're tied into quadratics because they factor. And so again, we didn't really talk about leading coefficient, but we know that there's two directions for a parabola, and it comes down to this a value, which is the same a that's here. If a is positive, what does the quadratic look like? Up. So if a is greater than 0, we know this guy went up. And when a is less than 0, so it means the leading coefficient was negative, what happened to our parabola? And because of unit 1, you now know why. What was the transformation we were doing here? Vertical reflection. Well, that's what we were doing here too. We just never talked about it in those words. But that's why it flips like this. It's a vertical reflection. Again, let's talk about the end behavior. So I want to know on the left what's happening and on the right that's happening. On the left, is this pointing up or pointing down? Up. And on the right? Up. So we call this up, up. So definitely different than our linear function. So what we're hoping to do is, after we look at all of them, is try to see a pattern that's happening. What about when the leading coefficient is negative? What's happening on the left? Down. And on the right? Down. So we call it down, down. So this was grade 10, this was grade 11. Unit 1 of this year, we talked a little bit about cubics. Cubics. What did the general shape look like of a cubic? Yeah, it's like a snake, right? That went through the origin, so it's got that snaky feel to it. It also had a standard form. We didn't really talk about it, a little bit, but not too much. And it's ax squared, or x cubed, plus bx squared plus cx plus d. And we can equate it to y, or we can equate it to 0. It doesn't matter. It's all still the same equation. So we interchange that y and that 0. And so a positive leading coefficient, what it means is this a value is positive versus when it's negative. So these you haven't really seen a lot of, so I'm going to draw it for you. When the leading coefficient is positive, it starts from the bottom, it has a max and a min, and then ends at the top. So it's got that snaky feel to it. What about when the leading coefficient is negative? Well, that's just this flipped upside down. So this comes from the top, has a min and a max, and then goes to the bottom. End behavior. What's happening on the left? Down. And on the right? Up. For the second one, when it's negative, the left is going up, and the right is going down. Okay, we're only seeing the first 3. We haven't even done 4 to 5 yet, but do you see any patterns happening? Ooh, these guys are the same. Well, why is this one so different? These are the same, this one's different. Okay, let's carry on with our pattern. I'm going to come back to those in a second. Oh, somebody's already seeing it. X to the 4, they're called quartics. Because a fourth is a quarter, fourth of a dollar is a quarter, that's why they're called quartics. And their form is ax to the 4 plus bx cubed plus cx squared plus dx plus e, because we're not creative people, and equal to y or equal to 0, it doesn't matter. That's the general form of a quartic. Ax to the 4 plus bx cubed plus cx squared plus dx plus e. The other class said, one person said, that this was x to the little thing that's a 3. Yeah, it's x cubed. And I told him to tell his university professors he was homeschooled, just saying. It's not an x to the little thing that's a 3. It's an x cubed. Okay, if the leading coefficient is positive, it starts from the top. It goes min, max, min, back up. Hello, letter W. There we are. We had the x, or we had the u for parabola. We had the v for absolute value. There's our W. What do you think it's going to look like when the leading coefficient is negative? It starts from the bottom, max, min, max, back down towards the bottom. It is the M. It's kind of like a McDonald's symbol. Yeah, it's more curvy than that, though. It's like waves in the ocean. End behavior. What's happening when it's positive? What's the left doing? What's the right doing? Up, up. What's happening when the leading coefficient is negative? Okay, well, that didn't follow our cubic. Let's just flip back. Where have we seen that before? Up, up, down. Oh, the second one. So the first and the third are the same, and the second and the fourth are the same. What do we call the fifth degree of 5? Quintic. If someone has 5 babies at one time, what are they called? Quints. 5 babies at one time. I'm totally going to pause to tell you a story that has nothing to do with what we're talking about. Quintic also has a general form. I know you'll be shocked by the pattern here. It's ax to the 5 plus, want to take a guess? Bx to the 4 plus cx to the 3 with the little thingy plus dx squared plus Okay, let's see if you figured out the pattern. What do you think the end behavior is going to be? Up, down, I heard someone say. Down, up, I hear someone say. So it's probably going to be opposite. Is it going to follow the 1 and the 3 or the 2 and the 4? So it's going to start down and it's going to end up. How many max and mins is it going to have? Well, let's just look at the pattern there. Linear, no max or mins. Quadratic, as you know from grade 11, has 1, a max or a min. A cubic has 2, a max and a min. A quartic has 3, either a min max min or a max min max. What do you think is going to happen here? 4 of them. So it's going to start from the bottom. Max, max, min, end at the top. Crazy, looks like a camel. Okay, when the leading coefficient is negative, what do you think the end behavior is going to be? Up, down. How many max mins is it going to have? Still 4, so it's going to start from the top. Min, max, still looking like a camel, pointing down. We could do an x to the 6, which doesn't have a fancy name because we stopped naming them after 5. If we did an x to the 6th, what do you think the end behavior would be? Up, up, down, down. How many max mins do you think it would have? 5. We could do an x to the 7 if we wanted to. That'd be crazy because they're a buttload of work. But let's just pretend we wanted to do an x to the 7. What would the end behavior be? Down, up, down. How many max or mins would it have? 6. We could do an x to the 20 if we were really feeling crazy. What would the end behavior be? Up, down, down. How many max or mins would it have? 19. Here it is summarized in words. The end behavior of an odd polynomial graph. What's an odd number?
3.
Yes, more specific a definition. Ends in 1, 3, 5, 7, 9. So any of the exponents that have odd numbers, if we're a positive leading coefficient, the left-hand side goes down, while the right-hand side goes up. For a negative leading coefficient, the reverse is true. The end behavior of an even polynomial graph. For a positive leading coefficient, the left-hand side goes up, while the right-hand side goes up. For a negative leading coefficient, the reverse is true. The number of max or mins. The number of max mins for a polynomial of degree n is n minus 1. Example number 1. We're not even to the graphing yet. We're just going to talk about this end behavior, max min stuff, because that's going to help us when we get to the graphing. So for each function below, you're going to determine, is it a polynomial, yes or no? If it is, what's its degree? What's its name? Describe its end behavior, and the number of max or mins. So we'll do A together, and then I'll give you a few minutes to try B, C, and D with a friend. Is it polynomial? How do you know? What's the definition of a polynomial? Exponents are whole numbers. That's the only definition. You can have fractions everywhere else. You can have constants. You can not have constants. You can have coefficients. You can not have coefficients. The only thing you care about is the exponents. What's the exponent on the x? Is it a 1? Is that a whole number? So yes, it's a polynomial. What's its degree? How do you know that? What's the definition of degree? Largest exponent, and the largest exponent we have is 1. What's its name? What do we call him? Linear. End behavior, I'm going to abbreviate to EB. If you don't think you're going to remember what that is, write out end behavior. So we just need to think back to those patterns. If it is an odd polynomial, we need to look at the leading coefficient. What's the leading coefficient? 1/3. And we don't care it's a fraction. That's fine. All we care is a positive or negative. Is a third positive or is it negative? Positive, so you need to think of a positive line. What does the left-hand side do? It goes down, and the right-hand side goes up. Because I'm visual, I tend to draw the line off to the side so I can see it. If you're not visual, you might not need that, but I like to look at it to see the end behavior. And max/mins. Well, that's easy. We just take the degree and minus 1. What's the degree minus 1? Which makes sense. The line doesn't have any max/mins. Find a friend, do B, C, D together. We'll talk in a couple minutes. I'm not going to write because you got it written. We'll just talk. So B, I heard a few people like whisper, 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 like, what's going on? Yeah, it's radical, right? We've done those before. It's got a square root. And square roots, don't forget, from grade 10, are really exponents in disguise. What is root of x as an exponent? Not quite. Root of x becomes x to the 1/2. So radicals are always fractional exponents. And so if I wrote that as x to the 1/2 minus 5, could that ever be a polynomial? No. So radicals are radicals. Don't second guess yourself. They're not polynomials. Oh, I see some people changing. So that's a no. It's not a polynomial. Done. Doesn't have a degree, doesn't have a name, doesn't have anything. It's a no. C, is it polynomial? Yes. What's its degree? 2. What's its name? I'll accept 2 answers. Or, yes, not parabola. The end behavior? Down, down, because it's a negative parabola. And then what's the number of max/mins? 1, degree minus 1. 4, or D, is it a parabola? Is it a parabola? Is it a polynomial? Yes. What's its degree? Good job. Anyone get caught on the 4 there? Yeah, you got to make sure you look through all the terms, because sometimes they won't put the biggest one first. So don't just look at x to the 4, oh, that's the biggest, because the second term has an x to the 5. So it's a degree of 5. Tricky, tricky. I tricked the magician. I'm kind of happy, actually, a little bit. Didn't see that coming, did you? What's its name? Quintic, because of the 5. What's the end behavior? Well, the quintic is negative, because it's a negative 3 in front. Up, down, and how many max/mins? 4. Questions on this, because this is the first couple steps when we actually go to graph in the next example. Okay, let's do some graphing. Methods. I'm going to circle the first three and put a little star. And you can make a note off to the side is these are really thinking steps. There's nothing you have to write for steps 1, 2, or 3. I write stuff because I'm visual. But if you can just picture this in your head, there's no work you have to give for steps 1, 2, or 3. The work actually is step 4 and 5. So however that makes sense to you. You don't have to put stuff down. I do because I'm visual. But if you can picture it in your head, no big deal. So step number 1, the very first thing we do is we name it. Then we think about the coefficient and the end behavior, then we picture the graph. What that does is before we do any calculations, already gives us a picture of what the graph should look like. Okay, so number 2. Is it a polynomial? Yes. What's its degree? Cubic 3, so it's a cubic. What's the end behavior? Up, down. What's the number of max mins? 2. So I, again, don't write out all of that. What I do is I just draw myself a little cubic. So I know it's up, down. I know it has 2, 1 max, 1 min. And I think about the fact it's a cubic. You don't have to write that again. Steps 1, 2, and 3 are really just thinking questions. But before I've done any calculations, before I've even calculated the intercepts, I know now where the max and mins roughly are going to be. The min is going to be on the left. The max is going to be on the right. It's going to come from the top, go to the bottom. So I already have an idea of the graph. Step number 4 is where you really start to show the work. So I'm just going to put step 1, step 2, step 3 all together just to say that we did that all in our head. Step 4 is we just calculate intercepts, just like you've been doing since linear functions in grade 10. I always start with y-intercepts because I find them easier. What's the definition of a y-intercept? X is equal to 0. So we go to the function, and we put in 0 every time we see x. I, again, would normally not write this because that's fairly easy to do in your head. I'm just writing it because it's first example. But if you can look at it and see that you're going to have 0, 0, 0s, all the terms, and y equals 0, that's a-okay. Okay? And again, just like before, I like to put 0, 0 as a coordinate to show myself later that's a point I'm going to have to graph. So if you just wrote down 0, 0, that would be enough to get the mark for that one. You don't need to show all that work. X-intercepts. What's the definition of an x-intercept? Y is equal to 0. Everything else stays as is. Oh my God, it's cubic. How do we find the x-intercepts of a cubic? Well, we factor it. How do we factor a cubic? We use a theorem to guess and check one of the values. Once we have one of the values, then we use synthetic division. Once we have the answer from the synthetic division, we factor it. If it's still cubic, we keep going. So this is why we've done everything in this unit, is to be able to find the x-intercepts. That's where everything has come from. So guess a number. I heard someone say 1. Okay. Again, you don't need to show that. I'm just doing all the steps for the first example so you can see what's happening. Exponents come first, so 1 cubed times the negative in front, negative 1. 1 squared, 1 times the negative 5, negative 5. Negative 6 times 1. Conclusion, sad face. I don't even care what the number is. I'm not even writing it down. I don't care. I just know it's not 0, and that's not good. Okay, you want to try negative 1? Sounds good to me. Exponent first. So negative 1 cubed. So negative 1 times negative 1 times negative 1. And then I've got another negative in front. Positive 1. Negative 1 squared. 1 times negative 5. Negative 5. Negative 6 times negative 1. Conclusion? Sad face. Yes, I feel like this sucks too. This is just the way the questions work. If there was an easier method, I would have shown you the other day. Okay, now what? Negative 2 cubed. Negative 8, and then we have that another negative and another negative. The other negative in front, 8, positive 8. Negative 2 squared, 4 times negative 5, negative 20. Negative 6 times negative 2. I heard some excitement in that 12, because what do you see? Yay, happy face. Again, like I explained before, I like to write the factor here just so at the end we don't forget him. Because what happens in this case, if you forget him, you've forgotten an x-intercept. And that's obviously really important to the graph. So I like to just have him hang out there so I remember he's there. Okay, now what? Synthetic division. I feel the same. Yep. What number's going to go on the outside? Negative 2. What needs to go on the inside? So there's two things you need to check when you're doing your synthetic division. What were those two notes from last class? So check the order. Missing terms. So look back at the question. Are the terms in the right order? Are we missing anything? We're missing a constant, but does it matter if we're missing at the end? Won't matter. So it's only if you're missing stuff in between. Again, you could put a 0 for a constant. It won't change the question. It's just one extra step. So what are the numbers that are going to go inside? Negative 1, negative 5. And again, if you wanted to put the 0, you could put the 0. It's not going to change anything. Drop the negative 1. Negative 2 times negative 1. Add negative 5 plus 2. Multiply negative 2 times negative 3. Add negative 6 plus 6. And I'm just going to highlight that because he's our little built-in check. What's the check there? What did we talk about last class? He has to be 0. If he's not 0, you've done something wrong. Okay, so what's the answer from this? Okay, got to factor him. This is the type of factoring you're the worst at. I don't know why. It was the very first one we taught you, and then we taught you all those other ones, and it just made your brain freak out. If there's two terms, it's probably common factor. Probably common factor. Is there anything common between them? Negative x, so let's take him out front. So negative x squared divided by negative x. Negative 3x divided by negative x. So you might want to make a note, usually common factor, when there's two terms and you can't do anything else. And then we just take this polynomial and we smush all those pieces together. So I have the negative x, the x plus 3, and my guy from way out here, the x plus 2. That's where we stopped last class because we were just practicing factoring. We were done. But now we're going one step further and we're finding the x-intercepts. How do I find the x-intercepts? Well, this just becomes a split and solve. And there's just 3 pieces now instead of 2 like we had with quadratics. So I have negative x equals 0, I have x plus 3 equals 0, and x plus 2 equals 0. How do I get rid of the coefficient of negative 1? Divide, so 0 divided by negative 1, it's just 0. And so this is the point 0, 0, which isn't a surprise because we had that up here as the y-intercept, and if it's the origin, it has to be an x-intercept. If x plus 3 equals 0, what does x equal? And so that's the point, negative 3, 0. And if x plus 2 equals 0, x equals, and so minus 2, 0. Okay, so I got my y-intercept up here. I got 3 x-intercepts, which is really cool. Grabbing a sticky note. This is 0, 0 for my y-intercept. Also for my x-intercept. Negative 3, 0. And negative 2, 0. I put it at negative 1. I'm sorry, I'm left-brained. I have to get a whole new sticky. Let's try that again. 0, 0, negative 3, negative 2. Then what I do is I grab this guy up here, and I wouldn't normally write this on my paper. I'm just doing it for this example. And I grab a pencil, and I start to fill in. I know it's got to come from the top. I know it's got a min somewhere between those 2 first x-intercepts. I know it's got a max between the second 2, and I know it goes down. I'm just going to zoom in so you can see that. And I'm doing it in pencil because I'm going to erase it once I find out the exact points. But I know that has to be the general shape because it's cubic, because of the end behavior, because of the number of max mins. What I don't know is the height of the max mins. I don't know, is it really shallow? Is it really long? Is it really high? I don't know the height. That's the only thing I'm missing. Well, how do we find the y value of any point on the graph? Test points. Step number 5. The book says table of values. That's why I wrote it. I would call them test points. So if that makes more sense to your head, you can add that in step 5. Completely up to you. What test points am I going to use? Well, let's look at these 2 little intercepts that are really close together. I know that the min or the max, in this case the min, has to be halfway in between because it's symmetric like a parabola. What's halfway between those 2 x-intercepts? So negative 3 and negative 2. What's halfway? So I'm going to test negative 2.5. So we go back to the original question, negative 2.5 cubed minus 5 times negative 2.5 squared minus 6 times negative 2.5. Oh, you can't see that. This would be a calculator question. I would never expect you to cube 2.5. If I remember from the other class, I think it's like 0.6 or 0.8 off the top of my head. It was 2 days ago, so I'm guessing. You can't just like magically pull a calculator out of your sleeve. Like here, it's in my ear. Oh, that'd be really cool. Thank you. Like, no pressure. Like, don't hurry because the bell's about to ring. Like, take your time. It's okay. It's all good. Sorry? For 2.5 cubed? I'd have to, I can't do that in my head. It's 8 and then point, no, it's got to be less than that. Because 0.5 cubed is 0.125, 8.125. And then times a negative, yeah. I think it's 0.8 or 0.6. It kind of sticks in my head. Oh, negative 0.6. Can we do to one decimal place? So this is the point, negative 2.5, negative 0.6. So it's a little tiny min. The max I know is between negative 2 and 0. What's between negative 2 and 0? And we actually did that way up here when we did a test. So if we just figure this out, we know the answer. It's 2. And that's all I need. I know my cubic comes from the top, goes through that little tiny min, goes through that max, and goes towards the bottom.